Okay, so this is a nice paper from a new franchise called Nature Computational Science. You know, Nature is making up so many franchises now. It had Nature, and then came Geoscience, Climate Change, now Nature Cities, Computational Science, Nature Materials, Nature everything, right? So the paper is relevant for us climate scientists because it talks about uh, digital twins for making disaster management decisions at the rapid crisis management scale as well as the slow adaptation and policy scales, and uses the kind of takes off for I'm fumbling words. It's a kind of a take on Daniel Kahneman's book Thinking Fast and Slow, which won him a Nobel Prize, behavioral economics issues. Thinking fast and slow in disaster decision making with smart city digital twins. Many cities are vulnerable to disaster related mortality and economic loss. Smart city digital twins can be used to facilitate disaster decision making and influence city policies, urban policies, but first they must accurately capture, predict, and adapt to the city's dynamics, including the varying pace at which changes unfold. So it's obvious smart cities, of course, you imagine that it's got well wired up so that you can track everything and make decisions properly for buildings, transportation, extreme events, floods, heat waves, urban resilience, everything, right? Cities are increasingly subject to stressors such as heat waves, hurricanes, wildfires, coastal sea level rise, tsunamis, windstorms, and epidemics. Close to 60% of the cities with a population greater than 300,000 are facing high risk of exposure to cyclones, floods, droughts, and earthquakes, as well as landslides and volcanic eruptions, with a high degree of vulnerability to disaster-related mortality and economic loss. So that's 60% of the cities with populations greater than 300,000. You know that there are many megacities from Tokyo to Beijing to Kolkata, Mumbai, into west all the way into the US, New York, Chicago, and so on. So obviously there is a lot of vulnerabilities and exposure, and planners and policymakers can play a critical role, and climate scientists are always jumping up and down saying how we have all this great information but they are not being used for decisions. Of course, decision makers know how useful the actual information we produce is. We need hyperlocal risk information with kind of details for accurately capturing, predicting, and having a projection of decadal prediction of cities' dynamics. The climate is just one aspect, right? There is demographic, economic activities, and of course poverty. You can think of many socioeconomic factors that have nothing to do with climate. So climate is a stressor on top which can exacerbate things, and we have to plan for it. So effective data-driven decision making, whether it's during preparation or recovery during moments of crisis or in the midst of an ongoing disaster, requires a robust capacity for capturing city dynamics. So it's not just climate, it's the city dynamics with or without a climate stressor, but often with a climate stressor like cyclone, hurricane, floods, etc. Right? So this entails recurrently sensing and modeling the state of the infrastructure, human activities unfolding over and enabled by the infrastructure. People may congregate in places like malls because it's available, and there are complex interactions with transportation. People may even go to malls because it has air conditioning, and at home they may not have it, and so on. So predicting the states of stability and change, so the evolution of urban systems becomes important. So there is a widespread proliferation of sensor installations now, more and more awareness, and everybody thinks data will help, and it will, and at the availability of unprecedented levels of data isn't necessarily improving the decision making. So computational approaches in capturing, predicting, reacting, and adapting to changes in the state of our urban systems still need to mirror the pace of change for that promise of smart cities and data about human infrastructure interactions to lead to better decision making. It will happen over time, but there is still a lot of work to be done. So fast and slow urban dynamics in that sense, change processes in urban human infrastructure systems do not occur on a single time scale. Obviously, when disasters happen, there is a response needed. So transport construction can take decades and then end up being not optimal. For example, Mumbai looking at is building lots of metro lines, and construction snarls traffic jam, creates traffic jams everywhere, and so on. So there are fast fluctuations like daily mobility, so traffic jams, bottlenecks, and failures of public transportations, etc. So the changes unfold based on these slow and fast time scale infrastructure developments. So control responses to these changing phenomena also are needed at varying cycles of change, and they are driven by the urgency of the decision at hand. If there is an accident and could be a disruption by intentional acts of terrorism or something as well. So it can invoke all kinds of emergency decision-making needs, and yet the longer-term thinking has to have that in mind in terms of resilience of the system, right? So managing highway throughputs modeled for routine operations demands a slower pace of decision-making than during emergency evacuations when throughput capacities are impacted by the emergency event such as flooding during a hurricane. So this is coming from the Western world, but global South can face other issues. Many cities are not necessarily facing cyclones all the time like Mumbai, but it's facing a lot of the other problems. So we'll look at figure 1 as for a conceptual fast and slow change processes in the real world, and data-driven disaster decision making is analogous to Daniel Kahneman's Nobel Prize winning research on human decision making and the two fast and slow systems that support human decisions. So that's why they used that title. Kahneman's theory suggests that human cognition is governed by two systems. System 1, a fast mode of thinking driven by intuition and heuristic processes, and heuristic processes, and system 2, a slow, more analytical mode of thinking. However, data-driven disaster decision-making is driven both by decision-makers' thinking process and by the quality of the data-driven models in use that capture fast and slow change processes in the real world. Therefore, it's crucial that our computational models evolve to account for both fast and slow urban dynamics. Daniel Kahneman's book is quite difficult to read. It's a nice book if you survive it, but intuitively you can say there is intuition and heuristic processing. If I ask you what is 2 plus 2 or 2 times 2 or 3 plus 9, 9 times 3, you may have very quick answers because you just remember it. But if you say 13 times 23 or 13 plus 169, you may slow down and you have to think through it. So there are intuitive processes and there are fast processes that require slowing down and thinking about it. So here is the fast and slow disaster decision making dynamics. You have on this scale slow things and fast things. So earthquakes can be very rapid and things unfold very quickly. It may last just a few seconds, but create a disaster that will take sometimes years to recover from. There are rapid responses of saving lives and removing people from under the rubble and so on. Tornadoes also fast. Tsunami, of course. There was a big tsunami scare recently with the the Russian earthquake, but fortunately not much happened. Flooding and droughts, on the other time, are relatively slow evolving and slow response kind of systems. So in a digital twin, you have the smart city concept. So that's your digital twin, which is basically a computer model of everything down to a street level and a pothole. And then a signal comes fast and slow, as you can see here. And then there is some decision making with multiple time scales, which has to then make the city really as smart as it is supposed to be, right? Fast onsets such as tsunami, earthquake, and tornado, and slow onsets such as flooding and drought disaster events result in change processes in real cities that may vary in terms of the pace and duration of change. Heterogeneous data needs to be captured at mixed frequency and integrated into smart city digital twins, as we see here as SCDT models in real time at corresponding frequencies that change processes are taking place. So it's not just collecting weather data, but you need to collect all the data, and the models have to also be able to handle all this data to feed back the bite-sized information for decision making that is coming at real time, near real time, or slower time based on the process involved, fast or slow. Both fast and slow modes are integrated into SCDT model, into the same SCDT model, which is progressively updated in parallel with changes in the real world. So it's not a fixed model, it's very adaptive and flexible, and it gets updated. SCDT informs decision makers, who must be a combination of fast and slow thinking, to adaptively devise interventions at various levels of urgency. Decision makers generate time-critical decisions that impact the real environment, and the cycle continues as new interventions and ultimately new policies/strategies generate new change processes in the real world. Okay, so it seems very intuitive, and yet designing such a system takes a lot of work. So this paper tries to make a few points about that. So when change is fast, then you want the model to capture the real world, and it's critical, of course. And you need to provide information in real time, near real time. So climate predictions on scales of years to decades, we rely on slow retrospective data with lower levels of uncertainty. But as the pace changes, so flooding on the scale of minutes to hours. So in this context, it's slow, but in the context of weather and climate, it's still fast. So we are faced with higher levels of uncertainty coupled with curtailed response time. In other words, when change is fast, for example, in the event of an earthquake, rapid response relies on the quality of data-driven fast decision making, exactly where the epicenter was, where the maximum damage is, and how broken systems like networks, power, and water pipes are going to affect the evolution of the earthquake impact. So this is informed by the speed of capturing and predicting the states of change in the real world through real-time and predicted data, as we can no longer only rely on retrospective data. So earthquake happens, effects begin to cascade, people are trapped, roads are damaged, bridges have collapsed, and so on. So you need some observation system that's capturing all that at the speed that it needs to be, and is feeding to the digital twin that is running, hopefully not damaged, and then decisions have to happen quickly, and then some predictive information is needed on how things will change. Like, for example, if a heavy rain event is coming on top in the next few days or so, right? So timely predictions of weather variables, so cloud cover, etc., can enable short-term weather, especially severe weather predictions. Predictions on the scale of minutes and hours are essential in informing early warning systems, enabling rapid emergency responses, initiating timely communication with communities, and so on. And there have been thousands and thousands of weather-related accidents around the world. This is talking about US, but timely predictions are, of course, critical, and we tend to focus from the climate science a lot on those and think that's everything, so we keep on hammering that we need to do that. So we are not necessarily thinking of fast and slow time scales, we are thinking about adaptations and urban infrastructure building with climate change in mind. but you can see that there are many other factors to worry about. So smart city digital twins, SCDTs, then it's a promising approach, of course, and they are living digital replicas of a city that are continuously updated with real-time data and analytics on interactions between humans, infrastructure, and technology, which can offer more holistic views of the changes that take place in a city. So that's kind of a formal, informal take on exactly what smart city digital twins mean. But this idea of smart city has become a little too generic now. Nobody knows exactly what it means. And basically, learning by doing is the approach. So you keep on instrumenting and linking up through IoT and so on, and decision makers have to be trained to use that data flow, information flow to make decisions at smart and slow time scales. So they couple real and simulated versions in the idealistic world and create synergistic feedback loops between the slow and fast systems, offering promise of a real-time decision-making support for smart cities. As often it is about infrastructures and real and simulated versions. So you are looking at what's happening, trying to make sense of what's happening in the digital twin, and digital twin should also say what will happen in the quick, fast time scales and slower time scales, right? As it evolves in parallel with the real system, CDT enables hyperlocal decision making through monitoring, assessment, and what if scenario predictions and adaptation across urban systems. What if scenarios are very critical, because if you are going to build a mall or a new housing complex or a school or whatever, you want to see how the effects cascade into water quality, air quality, traffic systems, and other facilities, hospitals, airports, etc., and then hopefully make more robust and optimal decisions by doing that. So that's kind of a slow strategic timescale decision, whereas then you have to see how, once you did it, the fast timescale decisions will be needed to be adapted to the new developments in the cities. That's why we call it a dynamic system. So such capacity, though, requires digital twin to be progressively cognizant of the pace and magnitude of the change processes across urban human infrastructure systems at varying timescales. So planners, policymakers, and government officials are not only faced with the dyad of fast and slow decision making, but also with a range of in-between layers of transitional states across all phases of the emergency management cycle. So like mitigation, preparedness, response, and recovery for earthquake, having building codes for earthquakes or floods, and then being able to mitigate flood risks, and then being prepared, response, recovery, etc. Right? Resilience is often about recovery, but also flexible recovery, so that you are not trying desperately to go back to the previous functionality, but adjusting to the new reality as well. So while planners may be well prepared to make decisions on slow changing phenomena related to preparedness and devising mitigation strategies, control decisions made during fast changing response times can very well generate new feedback loops of human infrastructure interactions that would challenge the reliability of previous decisions made. Okay, so the pace of decision making goes beyond the threshold of urgency, and the influencing factors become dynamic when then SCDT needs to be able to adapt and autonomously capture and predict across a dynamic range of changing phenomena. So the SCDT has to in some ways also give you decadal prediction of the smart city system itself, not just climate. We worry about climate, but that is demographics, pressure on the infrastructure, and so on as well. So this will depend on whether conditions require preparing for, reacting to, or recovering from a disaster event. So we are building systems, disasters come, interactions happen, we learn something, and then we plan, because the disasters are evolving constantly because of climate change, and the risk landscape is evolving. So decisions are urgent nonetheless. We call it post-normal science, ambiguous, complex, uncertain world, but decisions must be made, right? Model synthesis and nowcasting, then synthesizing disaster dynamics across multiple timescales in SCDT decision-making models is critical in providing timely responses to various disaster control measures. So you need synchronization of SCDT with its physical counterpart, ideally done in real time or near real time, relying crucially on the availability of uninterrupted data from the real system. So disaster may knock off your data system, but then you need to have redundancy or plans to deal with the failures, and that's what digital twin can help with as well, right? Heterogeneous urban data that are progressively fed to the SCDT are obtained at mixed, so fast and slow frequencies. This can create substantial latencies and then can create data fusion process, complications in the data fusion process. But dynamic association of SCDT with the city at both levels of data fusion and predictive model generation, while incorporating all the endogenous and exogenous variables across fast and slow timescales, is complex, to say the least. Current understanding of the research community on how digital twins should best integrate heterogeneous data. So you have socioeconomic data, weather data, maybe health data, and transportation, etc., right? You have to synthesize all those things to lead to proper decisions in every context and every time scale. So in order to model these, in order for the modeling efforts to be based on a more complete understanding of urban dynamics across mixed frequencies of changing phenomena and driven by the desired pace of decision making, we must advance our understanding of the multi-time scale nature of digital twin dynamic modeling. So it's focusing also on how effective and flexible and responsive the digital twin model itself has to be. It's not something you build once and sit and look at all the time. Among dynamic models accounting for multiple timescales, a number of studies have shown that mixed frequency nowcasting models are capable of handling irregularities of heterogeneous data, so mixed frequencies and latencies in real time, and recursively updating predictions. So AI/ML plays a big role in that. So typically what you do is, I'll just digress a little bit, you make many simulations, let's say with the weather model and the climate model, and when actual flooding happens, you don't have time to run the dynamic model because it can take a very long time at a very high resolution where information is needed. But if you create simulations, then you can run emulators very fast to see what will evolve. That's what we would call what-if scenarios, but it's not just what-if scenario on a slow time scale, but also on a very rapid time scale. Right? Nowcasting, increasingly used in meteorology, economics, and healthcare, refers to an objective near real time, so plus to 0 to 6 hours estimate of current states and short-term forecasting. Relies heavily on the availability of rapidly updated high-resolution observations. However, current nowcasting models have limited representation of physical processes, and the object of interest is often a low-frequency variable such as a quarterly gross domestic product growth. So see how quickly we are mixing weather near real time and economic near real time as well. We lack scientific research investigating the applicability and scalability of nowcasting approaches in developing integrated predictive models of SCDTs for dynamic disaster decision making across both fast and slow timescales and across sectors. So infrastructure, health, economics, recovery of the socioeconomic activities, not just people movements, but you may need food to start coming in as quickly as possible, or other emergency requirements, and you want to make sure the roads can be quickly made operational and so on. So vector autoregressive models, for example, are widely used in macroeconomics to jointly model the dynamics of economic variables, despite the dependency of each variably on. Why am I fumbling this? Despite the dependency of each variable on past patterns of all other variables, patterns of correlation of the forecast errors in these models remain unconstrained. So some technical details there that I'm not going to get into, and I'm not an expert on it for sure. Such over-parameterization becomes problematic in the already high-dimensional setting of the SCDTs with both static and dynamic variables. Bayesian variables BVARs incorporate a naive prior model that assumes random walk evolution for all variables. However, the challenges of making inferences on the model's parameters in the face of data irregularities, so missing data, mixed frequency, and so forth, especially when nowcasting with large BVAR models, the challenge remains. Okay, so dynamic factor models. So suddenly we have gotten into economic models because Daniel Kahneman inspired article. So we are talking about digital twins, but still we are getting more into economics now. Dynamic factor models assume that observations of different variables in time are driven by few unobserved dynamic factors, and features specific to each variable are captured by errors. These models handle mixed frequency data by initiating the model at the highest available data frequency and treating the lower frequency data as a filtered version of latent high frequency data that are missing at certain intervals using likelihood based methods and Kalman filtering techniques. So we are mixing here. Dynamic factor models are not just economic models, and vector autoregressive models here is mentioned in the context of economics, but Bayesian approaches are very common to our business as well, especially when we want to use AI methods to either blend with dynamic models or just run them for short-term forecasts and so on. And Kalman filtering we use a lot for data assimilation as well, right? More complex models integrated with machine learning algorithms are particularly suitable for improving dynamic factor models by handling data with a larger number of possible regressions. Suddenly it's gotten very technical because it's a Nature Computational Science magazine, right? However, these models are effective for slower time scales, for example, seasonal predictions. In capturing disaster dynamics at a city scale, these models need to both scales to encompass the increasing dimensionality and control for exogenous variations along with their long versus short-lived effects. High dimensionality is often addressed by modeling by model approximation, which may compromise the SCDT's ability to capture interdependencies of human infrastructure interactions. So, it's not just something I can read off. There is a lot of technical details there I'm skipping over because I want to just relatively keep it short and give you an introduction to the topic rather than teach a whole course on it. So more recently, researchers have established promising mathematical foundations for digital twin modeling and coupling dynamical systems based on probabilistic graphical models integrated within data-driven analysis and decision-making feedback loops. Technical details again, but you can look up the reference. However, in order to achieve scalability for SCDTs, we are still challenged by the need for improved parameterization, inclusive of appropriate exogenous controls, reduced order modeling, and relaxation of model assumptions. So obviously that is, you have to follow up with the references for those details. If you're an expert, you may do that. If you're not, I hope you're getting the main points. So let's conclude anyway. Change processes across urban human infrastructure systems occur at not a single but a range of temporal scales, and we are faced with the challenging task of modeling a range of dynamic associations between SCDTs and the real city infrastructure. So the focus here is infrastructure, even though infrastructure has impacts on the economics and so on. Building on existing models that can, with limitations, capture irregularities of scale and mixed frequency data such as BVAR and DFM that we mentioned. Future research on digital twin modeling should advance in the direction of multi-timescale prediction as a critical next step in supporting dynamic disaster decision making. The bottleneck in this direction is encompassing increasing dimensionality while capturing mixed frequency data and controlling for exogenous controls with varying temporal effects. Okay, so just get a sense that disaster management is not just going to be about saving lives and livelihoods, but also worrying about infrastructure at fast time scales in terms of its impacts and its rapid recovery needed to continue the system back to functional or build the system back to recover the system back to functionality and so on. Investigating computational methods by which digital twins can best integrate heterogeneous data generated at mixed frequencies to model city evolutionary dynamics is central to this effort, inevitably. Dynamic modeling of SCDTs also escalates into the spatial dimensions, identifying the most relevant spatial scales and aggregations by which disaster dynamics and real-world change processing need to be captured is yet another poorly explored area of research. Future research should expand computational modeling efforts in all three dimensions of time, space, and frequency, investigating ways to control for both endogenous and exogenous change processes in urban systems. Understanding the multi-spatio-temporal scale nature of HCDT dynamics modeling is the first step towards providing timely decisions and responses to minimize disaster-related mortality and economic loss. So, mortality is always an issue that gets a lot of attention, but there are many other issues in terms of just relative mortality of natural hazards versus, let's say earthquake, which is a natural hazard, could be low probability but high impact event, whereas you could have relatively higher probability and lower impact events like floods. Earthquake may kill many more people than floods because preparing for earthquakes in the slow time scale may require many more decisions in terms of building codes and so on compared to flood mitigation, right? So all these have to be considered in digital twins. So I hope it helps. I learned a lot and I tried to translate for you, and tricky thing always is we have to learn these things because this relates to our business, and yet we have to deal with things that are not immediately in our domain. That's what interdisciplinary research is all about, that you have deep expertise hopefully in one direction, but you are able to assimilate all the related disciplines for improving your own contribution. I don't know why I'm being philosophical, but anyway, see you in the next podcast.